We are with unit 6, or excuse me, unit 7, lesson 6, and we're working on what about other bases. So we're going to explore patterns with bases other than 10. And in this lesson, we're going to continue to use our exponent rules for bases other than 10. We've talked about product of powers. Just do a quick review of this. Product of powers is any number times same base, means that I can simply take the exponents and add them together. We've talked about quotient of powers, which means that when the bases are equal and I'm using division, I can find the difference in the two powers. And we've talked about power of a power. So meaning that the power of a power is that I can take the base, as long as it's there, I can take the exponents and just multiply the powers together. So we're going to extend this lesson a little bit more to following a few other pieces with this. We're going to see what happens with zero and negative exponents. And we'll go from there. Okay, so the first thing we're looking at is true and false. So if we look at these 3 to the 5th power 3 to the 5th power is less than 4 to the 6th power. We can use a little bit of logic to help us out with this. First off, recognizing that if the bases are different, recognizing that 3 and 4, 3 is less than 4, being multiples of 3, 3 times 3 times 3 times 3, is not going to grow as fast as 4 times 4 times 4. What we understand with that is that there's a different growth rate, or what we call a constant ratio of multiplying by 3 and multiplying by 4. Not only is that the case, but also with their exponents, we're multiplying a smaller base not as many times as a bigger base. That bigger base is being multiplied more times. This one is going to definitely be true. The second one might catch you a little bit. You might be thinking, okay, we have a base that's negative. And that's true, we do, but take a look when we magnify that a little bit. If we recognize the opposite of opposite of 3, or we're saying the quantity of negative 3 times negative 3 is being compared to just 3 to the 2nd power. 3 to the 2nd power, remember, is 1 is our greatest common factor times 3 times 3. So 3 times 1, 2 times. And what we see on the left, negative 3 times negative 3 is equal to 9. And 1 times 3 is also equal to 9. So when we talk about these, we actually see that these two expressions are equal. So in this case, what we have to recognize with this is that we're dealing with something that's actually false. So we'll go ahead and get rid of this word and we'll write false, because both those expressions equal 9. And we can say negative 3 to the 2nd power is equal to 3 to the 2nd power. There's our reasoning for being false. Number 3, you might be thinking, well, hey, why not? The last one was equal, so maybe this one is equal. What we want to look at with this one, let's put our work over here. Negative 3, what is the quantity of negative 3? 3 times is said to be equal to 3 to the 3rd power. Now what we see with this is the previous one, we saw that negative 3 times negative 3 is 9, positive 9. So if we move past that, from that part, that's positive 9 for that product, and then we multiply it by negative 3, then we end up with negative 27. Whereas on the right side, 3 to the 3rd power is 27. And so what we find out is that is not a true statement. This is a false statement because the expression 3 to the 3rd is greater than the quantity of negative 3 raised to the 3rd. Okay, and finally 5, the quantity of negative 5 squared is said to be greater than the opposite of 5 raised to the 2nd power. So negative 5 times negative 5 we know is positive 25. But when we talk about the opposite of 5 to the 2nd power, then we want to be thinking about, we know 5 to the 2nd power is 25. But we think about the opposite of 5 to the 2nd power has to be 25. So in this case, this is a true statement. Remember that negative sign also means opposite, and doesn't always mean negative when we're working with it. So when we go to the next step of this, we say what happens with zero and negative exponents. So it's bound to happen at some point that we're saying, well, what happens when you hit 0 for an exponent, and what happens when you get to the negatives? We are going to see that right here with this table. We recognize this table is meant to show what happens when we have those exponents that are 0 and negative. So we start out here, again, this table seems kind of backwards. We go from right to left. We're going from a large number to a smaller number. And so, I mean, that's where we have to deal with it. That means that going from right to left, we're always increasing by a factor of 2. So every box, every value that's inside of those boxes becomes a value that says that it's twice as big as the previous box. So we have a couple of things that we need to understand as these parts when we go to work with these things. And I don't know where my tools just went. So let's see if I can figure out where to find them. I'll just switch over and use these ones. So when we're talking about these pieces, oh man, now I really messed it up. Okay, let me try and see if I can fix it. I apologize for this. Well, guess I'm redoing it. Or not. Okay. I guess I can't zoom in to lose my stuff. So sorry for the weirdness in the video. I guess it just fits with every time that I do a video. So here we go. Let's go back in here. We'll use our new pen and let's start talking about this. So the value of 16, we know that we went from the previous box to this box and we got 16. So we multiplied some unknown number times 2 to get 16. It would make sense that then that number would be half of what it was previous. So what we have with that pattern, as we move toward the left, each number is being multiplied by 2. So maybe we should start over here at half. 1/2 times 2 would be 1. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Okay, cool. Well, what I know about these ones then, if I work backwards, then if I take my half of a half is 1/4, and half of a fourth is 1/8, and half of an eighth is 1/16. That's great. So I just worked my way backwards. And what I see is really kind of cool, or what I think is kind of cool, is I recognize a pattern that surrounds the 1. I see that on the left side, I've got a 2, but on the right side, I've 1/2. And then I have 4, and then I have right here, I have 4, and then 1/4, 8, 1/8, 16, 1/16. That's kind of an interesting piece for me. So let's see what happens when we get into the exponent powers. So as we look at exponent powers, we know that 2 is the same thing as 2 to the first power. So it seems reasonable that on the next one, 2 to the second power, that's going to make absolute sense because 2 times 2 is 4. And on the next one, we have 2 to the third power. So as we look at this and we start thinking about what kind of patterns we can recognize, we'll start to see where this power of this, or where this notion or this information about 0 and negative exponents comes from. As we start looking at the value for our powers of 10, our powers of 2, we see that 2 to the fourth power dropping back is 16 dropping to 8. So we can see that as our multiplying by, or our multiples of a half. And if I continue to take 1/2 each time, I continue to drop further and further. You might be saying, well, isn't that the same as dividing by 2? And yes, it is, but we're going to be thinking in terms of half. So the pattern goes 2 to the fourth, 2 to the third, 2 to the second, 2 to the first, which means 1 is equal to 2 to the 0. And 2 to the negative first is the same thing as a half. 2 to the negative second is the same thing as a quarter. You get the idea. And there's actually some bigger ideas that are coming along with this. So pay attention to that. Look for those patterns that we see here and see what happens. So as we move move towards the left, each number is multiplying by 2. But what's the multiplier as we move to the right? We saw that was a multiple of 1/2. We finished the patterns. If we're going to write 1/32 as a power of 2 with a single exponent, that means that we're going to have to step out with this one to the next level. We know that that's going to be 1/32 would be half of that. And so 1/32 would have to be 2 to the negative fifth power. So we could write that right here. And then what's the value of 2 to the 0 power? Well, we see that 2 to the 0 power equals 1. There's an interesting rule out there that goes with this. Any base raised to the 0 power equals 1. Always and forever. And it's for the reason of recognizing these pieces that there's a lot of depth to this, and we'll get to that here in a second. So from the fraction, or from the work that we've done with negative exponents, how would you write 5 to the negative third as a fraction? What we recognize with 5 to the negative third is we have to consider this. Like if we look for a negative third, we see that we came with power of 2. When it was 2 to the negative third, it equaled 1/8. Something to recognize, or something important that we can note, is to recognize that 1/8 is also 1 divided by 2 to the third power. So you see that what we're after with this is actually more than just looking at a pattern, but also looking at a rule that we can understand. And that has to do with the negative exponent. The negative exponent should tip us off to be thinking about this, reciprocal. A reciprocal is any fraction that has been inverted, meaning this fraction of 2 over 1 was inverted and then simplified to the third power. So the 2 divided by 1 would be a reciprocal, would take this as 1 divided by 2. Since it was raised to the negative third power, it would be to the positive third power. You might be asking, why didn't I put a third power on the 1? Well, because 1 to the third power is just simply equal to 1. And so we have, if we were to simplify this all the way out, we could put 1/8, or we could just leave as 2 to the negative, or 2 to 1 divided by 2 to the third. So when we extend that to look at this value, 5 to the negative third power, as a fraction, we write the reciprocal first of 5, and then we raise it to the power of 3, which simplifies or undoes that value. So we're ultimately recognizing that we're multiplying by 1/5 3 times. So 5 to the negative third power equals 1/5 times 1/5 times 1/5, which in essence is just going to equal, I'm trying to get some room here. What we'll end up seeing is 1/5 times 1/5 times 1/5, which is just equal to 1 to the third power, or 1, divided by 5 to the third power. And if you needed to change this to just a straight out plain old fraction all by itself, this would be 1 divided by 125. That was a long way to explain that. So we should be able to do this much shorter on the next one. How would I write 3 to the negative fourth power as a fraction? Well, 3 to the negative fourth power would be 1 divided by 3 to the fourth. And 3 to the fourth power is 81. So that would be my fraction. 3 to the negative fourth power is 1 divided by 81. Wow. All right, we're going to go on to the next section, talking about exponent rules with other bases other than 10. And so when we talk about this one, other than 10, we have a lot of rules. So we have this group of friends, Lynn, Noah, Diego, and Elena. They decided to test each other's knowledge of exponents with bases other than 10. And so each one of them chose an expression to start with, and then they came up with a new list of expressions. Some of the expressions are equivalent to the original and some are not. So it's our job to look through these lists and analyze and decide which expressions are not equivalent to the original expression and be prepared to explain. We are going to use a lot of the powers or a lot of the properties that we've been working with. We're going to review all of those here, and we're going to use those to figure out what these mean. So the first one, I see that this one would be power of a power. All right, and power of a power means that I can take the exponents and I can just multiply them together. I see that 5 to the third times negative 3 does in fact equal 5 to the negative ninth. So this one's good. It's true. For the next one, we're supposed to decide which ones are not equivalent. So we'll just circle the ones that are not equivalent. 5 to the negative ninth is equal to the opposite of 5 to the positive ninth. Looking at this one, recognizing that the bases are not equal, that one right away tells me this one is not equivalent to the expression. The next one, when we're looking at this is a quotient of powers. And under quotient of powers, we know that we can go ahead and subtract the exponents. Negative 6 minus 3. So this is 5 to the negative 6 minus 3. And negative 6 minus 3 does in fact equal negative 9. So this one's good. The next one is another power of a power. And I see 3 times negative 2 is 5 to the negative 6. So this right here does not equal negative 9. That one is out. We have 5 to the negative 4th minus the negative 5th, or divided by the negative 5th. And so this one, again, quotient of powers. We can recognize that and say, oh, okay, well, that's 5 to the negative 4th minus the negative 5th. And you might have been tempted to select this one and say, yes, it is equal. But the problem is negative 4 minus negative 5 is 5 to the first power. So this one I'm going to be circling in red again because that one is also not true. The last one is what we call product of powers. And under product of powers, we're taking the product of two bases that are the same. And so we can take their exponents and add them together. And negative 4 plus negative 5 is negative 9. So this one's also good. The ones circled in red are not true. The ones that are out there and about, they are good to go. So we've just reviewed the rules. Let's go ahead and see if we can go through this a little bit quicker now. Noah's expressions are given here. I see product of powers for 3 to the 5th times 3 to the 2nd. Adding those exponents would give me 3 to the 7th power. This one is not true. The next one, I see a power of a power. That means 5 times 2, which equals 3 to the 10th. This one's good. I see the product of 3 being multiplied by itself 10 total times. This is definitely 3 to the 10th power. 1/3 raised to the negative 10th power. Again, remember what we said about the negative exponent. If we see a reciprocal or we see a negative exponent, we need to think reciprocal first, which would make this 3 raised to the positive 10th power. This one is good. The next one, we see 3 to the 7th times 3 to the 3rd. That makes 3 to the 7th plus the 3rd, which is 3 to the 10th. That one's good. 3 to the 20th divided by 3 to the 10th is 3 to the 20th minus 10, which makes 3 to the 10th. And then we see another quotient of powers, 3 to the 20th minus the 2nd power. Because quotient of power says same basis, subtract the exponents. That's 3 to the 18th power. And then that means that that one is false because it's not 3 to the 10th. Okay, take a minute, go ahead and check number 3 and number 4. I challenge you to pause the video for a moment, try your own. And if you accepted my challenge, I'm going to show you which ones are true and which ones are false. This one is false. Just kidding. That one's not false. I got the wrong one. I meant the one next to it. Because negative 4 minus 8, this one is going to be x to the negative 12th. This one right here, negative 4 minus negative 8 is positive 4. The next one, true, false. That is 4 times x. That is not the same thing as x times x times x times x. This would be like saying that you have x plus x plus x plus x. And not the same as multiplying like this one right here. This is x 4 times. And then this one right here might throw a lot of people off. This one, you have to remember there's an invisible power right there of 1. And under product of powers, that gives us x to the 4th power. All right, looking into Elena. Hopefully you did actually take some time to do that. 8 to the 0 power. Remember that we said any number to the 0 power is always equal to 1. So 0 is out. Product of powers for this one, 3 plus -3 is equal to 1. Any number divided by itself is equal to 1. 10 to the 0 power equals 1. 11 to the 0 power equals 1. 0 is the only thing that we're going to cross off there because 8 to the 0 power does not equal 0. In summary, what we're after with this is we have 3 major rules that we just reviewed on top of a couple of little pieces with this. The first major rule is product of powers. Okay. The second major rule, do a different color, is power of a power. And then the third major rule on here is quotient of powers. And what would be really helpful for you to do to memorize these is recognize what is happening inside of the problem. We call this quotient of power because we are dividing powers. We call the product of powers just what it is because we're multiplying 2 powers and the outcome is a product. And we call the power of a power, the base is actually a power and it's being raised to another exponent. So that's why we call power of a power. These rules, they also work with powers that are less than 1. So when we're dealing with negative exponents or when we're dealing with bases that are less than 1, the exact same thing happens. It's really important for us to remember that negative exponents, we should be thinking reciprocal. So like this one right here, I'll get another pen. This right here is what we call the negative power. And what we have to focus on with the negative power is we need to think reciprocal. So reciprocal of the base. And then raise that to a positive power that was given. And then we have one final thing that we need to identify here, and that's this one right, this one right here is the 0 power equals 1. Okay, those are the major works of this. You will see this vocab when we get to the assessments. So please make sure that you recognize that you follow along with that you know what that vocab is. Understand the structure of what's going on with these powers and with these rules to be able to make the shortcuts with combining numbers that are written in exponential form. See you in the homework.